So we're looking at this problem?
Yeah.
All right. So the question is, how do we figure out the shear stress at the outer surface? Okay. And so for this, what's that?
The outer surface?
Oh, no. Oh, it's halfway between the center line. Okay. So the I think we talked about this before, right? But so the row that we're going to be interested in, at least for this problem, right? We have a D of, I just tried to get rid of that. Okay, the D is 1.4 centimeters. Okay, and that means that the C is going to be 0.7 centimeters, right? And that means that, let's see if we can get rid of that. Good. That the row of interest will be half of that C, right? So that'd be 0.35 centimeters in this case. Does that make sense?
Yeah.
Okay. So we want to know what the torque is, right, in between B and C. Okay. So to do that, the kind of the simplest way is to do the cover-up method, right, and cover up the left. So for that, right, what I would say is we have this open surface, and there is this applied torque of 2t over 3 still there, right? But then here, I mean, some of this is kind of extra, right? But we'll just say, okay, that's our plus z. Okay, so to obey the right-hand rule, then we're going to draw it going that way.
Yep.
And this will be what we'll call TBC.
All right.
Does that make sense?
Yep.
Okay, so if we want the shear stress, what we need is to use the torsion formula, right? So the torsion formula is going to be that gives us shear stress, correct? So T, we know what T is, right? Well, we kind of know, right? T is going to be 2/3 of this value, right? So T is equal to whatever 2/3 times. It's a little confusing, right? Because I have TBC, so maybe I should call it. Well, that's just a general torsion formula. So I mean, it's fine, huh? Okay, so it's 2/3 times 91 newtons here, right? Or 91 newton meters, right? And this is going to be TBC. We agree on that?
Yep. Okay.
So, and then rho is, like we said, 0.35 centimeters. Okay, so we'll go ahead and say, just to keep it straight in our calculator, okay, 0.0035 meters. And then J, we need to use C. Okay, so J is going to be pi over 4, and then we have 0.007 meters to the 4th.
I tried it where I redid the integral and I got some crazy number, but I also tried it that way and got it wrong.
Okay, well, I do not know. I do not know. I cannot see your work. I cannot see your work.
It was probably
But this is how I would do it, right? So then the shear stress is going to be this 2/3. Well, maybe it's just easier if I just write TBC, okay, rho over J. How's it going? Good. Okay, so that's how I would approach that one. Okay.
I'll give it a shot.
questions though? What we're going through here? And we can wait a second. Happy to wait a second before we move on to the next one. The next one you said was session 10Q4. Let's see.
I got a number in the thousands again. Is it supposed to be in the thousands at the MBA?
Well, I can check. No, it should not be in the thousands.
That's strange. Okay.
Yeah, the
The torque is already in Newton meters, right?
Correct.
So you just put it there as is.
yes.
Okay.
So let me go back. So let's go back here. Okay, so let's say hypothetically you have a torque of 80 Newton meters.
My problem is actually exactly the same as the one up there. It's just 90 instead of 91.
Okay, let's see here. Actually, I think you got a torque of 80 Newton meters, didn't you?
I started a new problem.
Okay, so what is the values that you have?
It's diameter of 1.4 centimeters and 90 newtons for the torque.
And a torque of
90 newton meters.
90 Newton meters.
Mm-hmm.
Okay, so here we go with our friend, the Google. Okay, so we'll have 2/3 times 90, right, Newton meters, times rho, which is going to be, so it's 1.4, right? So
Yeah.
that's going to be, oh, that's, it works out exactly the same, right? That we had? 0.0035 meters.
Mm-hmm.
Okay. And then we're going to divide by pi to the 4th times 0.007 meters to the 4th.
Wait, why are we using C?
Because that's what you have to use. That's the J for the entire thing.
Are you doing power of 4 or power of 3?
Or, sorry. Yeah. Sorry, that should be pi over 2. That's right.
Okay.
Yeah, pi over 2. Thank you for catching that. Okay, but it should be, we should still be using the C, yes. Pi over 4 is for I, which we'll cover later. Sorry. Okay, so that. Oh, I had to use Google. That's right. Because DuckDuckGo doesn't work as well. And we can do in megapascals. Yeah.
I was simplifying it wrong. I turned the C into a row, but I think I did 2 to the 4th instead of. I did C over 2 to the 4th. 2 to the 4th is, and I tried to simplify it from there, but it just didn't count. I don't even know what I did.
Okay, well, I hope that we were able to resolve part of the issue. Okay. Andrew, did you have any questions?
Yeah, with like the gear problems, and also we could do one of like the statically indeterminate ones with torsion.
Okay. Yeah, those are trickies. Those are trickies. All right. So let's go to the. I think Kira, you wanted we were talking about a gear problem, right?
It was session 10 question 4, yeah.
Okay. So let's. Okay. So this one, right? Oops, okay, so this question, system below has appropriately balanced masses. Okay, and you have shaft AB, this shaft here, and shaft. Oh, you need power.
My
Okay.
computer's gonna die.
Okay, got it.
Yeah.
And shaft CD. All right. All right here. Okay. So there are these two shafts. Okay. They both have diameters. Okay, of 1.1 centimeter. We have an M2 of some mass. We have acceleration due to gravity. We have length here, A2. We have length L2 for the shaft over here. We have a length here for this shaft over here. And we have a ratio of the radii, okay, R2 over R1. And we also have an elastic modulus. We have a Poisson ratio. And the question is, what's the angle of twist going from A to D in degrees? Okay. So what do we need to know? We need to know what the angle of twist is in the shaft here, and we need to know how much B is spinning, right? And that B, how much that rotates, better said, right, is going to be dependent on the transmission that we have here and how much this shaft twists. Okay, so for this problem, when we go from A to D, we're going to pretend that D is essentially fixed to the wall. Does that make sense, right? So, and it turns out that these masses have to be very carefully balanced, okay, in order for this thing to not rotate with acceleration. Okay, so let's think about this problem, and with maybe we'll let me see if I can do. What's the best way to do this? Okay. Maybe just take this little guy, put it over here. Whoops. Oh no. Oh no. Yeah, like this. All right. And of course, this problem, the answer is available in the solutions for the 2015 exam number 1. Okay. Let's see if I can. That's okay. I can write. Yeah, I got enough control here. Okay, so looking for angle of rotation A to D, essentially. And what we just said to get started is that if I know the angle of rotation from A to B, and I know the absolute angle of rotation for B, relative to ground, that will get me the answer, right? Yes?
So one question, so is the angle of rotation of B equal to the angle of rotation of the C gear?
So it's not equal to the angle of rotation of the C gear, okay, because there's a ratio, right? We do know that, but what is that? So since you asked it, right? So rotation of C equals what times, or let's do this, rotation of B equals something times the rotation of C. Okay? Well, let's do a little bit of thinking. In this case, it looks like gear C is smaller than gear B, right? And I think even in the way I wrote the problem, I did say that, did I say that the ratio, whoops, that's question 3. Yeah, okay. No, wrong. I'm losing things. Okay, here. Yeah, I said that R2 over R1 is 2.1, right? So, if gear C were to do 1 revolution, right, gear B would not do 1 complete revolution, right, because it's smaller, right? So the ratio here, okay, that you're going to get, phi B, is going to be less than 1 times phi C, and so that is just going to be R1 over R2. Okay, now remember yesterday we said if I rotate this wheel out, I get some distance d, right? So we're conserving the linear distance that would come out of the laying these gears flat on the ground, essentially. Okay, so that's one. Okay, so how else do you think we should attack this problem? Because that's an integral piece, all right?
Well, I guess finding A even, but then before that, I have one more question. So
Yeah.
why isn't the phi A to D? Why don't you also have to include the twist of shaft CD?
Oh yeah, we do. We are, right? But phi B captures all of that behavior.
Okay.
Wait, how come?
Because so when I write phi B, that's like relative to the ground of the earth. Okay? When I write phi A slash B, right, that's the rotation of A relative to B. Okay? So phi B means rotation of the earth. It means relative. It's like the absolute rotation. Okay, but phi B is going to have things inside of it, right? So we're learning what is phi B. Phi B is this times phi C. So then maybe another question is, what is phi C? And you're right, we need to know this one as well. Okay, but let's maybe let's start here. Does that sound good? Okay. So what is phi CD? Okay. And we're assuming that this is fixed. All right. Or what? Okay. Better said, what is phi C? Phi C is equal to phi C relative to D. Okay. And what is that? What is this is the twist, right, of that shaft. Now that's the deformation of the shaft. So what is the equation that we can use? We can just pop in an equation. I'm not saying we have all the numbers yet, but we can pop an equation in. So what is the equation?
So like TL over JC.
Yeah, JG. That's exactly right. So let's say that it would be the internal torque TD times this distance L1 over why J1 G. Okay. This is I need a little bit of help here. Okay. My hand was hitting this. Okay. So now I wanted to make that J look better, but I don't seem to be able to. I think Microsoft just had. All right, we'll keep going and then I'll reset it later. All right, hopefully that's clear. Okay, so what is? So now let's look at the this bar or this shaft here, CD, right? If I were to take a cut, okay, so let's say that I understand. Oh, it's not letting me erase anything. Okay, but let's say that I have this D, okay. And in this case, the external torque, at least if I've drawn it coming out, the external torque is actually twisting it that direction, right? All right. So that torque is like that. And what is that torque? That torque is just M1 G A1. Do you see that? Okay. Because you have this moment arm, and you have a mass hanging from it under gravity. So that's the torque applied on this end, which means that, you know, the internal torque like that is going to be equal to minus M1 GA1.
So the internal torque always goes positive to wherever the positive z-axis is? Oh wait, no, it's negative.
Well, yeah, it is, but I drew it that way. And in reality, it doesn't make too much of a difference here if it's positive or negative. Okay, and I think in the solutions I kept it as positive. Okay, but if we're being careful, okay, that would be it. Okay, and so what we have here, okay, is that TCD is equal to this TD. Okay, I mean, if I wanted to be more careful, I would have written TCD here instead of TD because it's really about the internal torque. Okay, so let's just write this out. This is going to be minus M1 G A1 times L1 over J1 G, like that. Now, that kind of gives us, so now you see we have a route that we can get to phi B. Okay, so now let's focus a little bit on what phi A slash B is. And that is an interesting question, okay, because we have this bar, or this shaft here, connected to this moment arm here. Okay? So the phi A relative to B, okay, will be whatever the internal torque TAB is, right, times L2 over J2G. Okay, and let's do the same thing. Let's look at a slice of A, right, or slice of, you know, between A and B here. So probably easiest to say this is going to be A. Okay, and if this is A, and I'm looking at it, right, the torque being applied here would be this direction, and this is going to be M2G A2. Right? Does that make sense? It's pulling it. Okay, we're good. So now, if I had a positive Z plus coming out of here, right, I would draw this torque, TAB, okay, like that, and this TAB, right, has to be equal to the M2GA2. Okay, so now I've got a way to write out like this. In order to figure out so I think, what do we not know? Do they tell us? Did I say, so we know what M2 is, okay, but we don't know what M1 is. Okay, so now we have to look at that relationship. Okay, so to do that, right, so we know M2, but we don't know M1, okay? And in reality, we don't need M1, right? What we really need is TCD, okay? So how do we do that? Well, let's draw out our nice gear system like that. Okay, let's say that, okay, if I look at this, and let's say I'm looking at it, well, I'm looking at it from the D side. Does that make sense? Okay, so I've got the big gear on the left and the little gear over here, right? This is like, you know, B, this is gear C, essentially, okay? So if I'm looking at it from that side, then what we can say is that there's a torque, okay? And this is the torque that we calculated out here, okay? So this torque is going to be M2GA2. Does that make sense? Okay, because it's causing it to go clockwise. Well, if it's causing it to go clockwise and everything's under equilibrium, that means there needs to be a force up going up on that to make sure on where in that location to compensate against it, right? So we'll call this force contact. All right, and therefore there's going to be a equal and opposite force, okay, acting on the smaller gear. Does that make sense? And this means that the torque that's resisting over here, this torque, we'll call it TCD, okay, has to be also balancing this force of contact. Okay, so here we have, this is radius 2, this is radius 1, and we can write out that M2GA2 is going to be equal to F contact times R2, and M, or we'll just call it TCD. It doesn't. TCD, right, is going to be equal to F contact R1. Okay, what's the same here? The F contacts are the same, right? So now, what we're interested in is TCD, right? So, so it probably makes sense to write TCD is equal to this F contact, which is going to be M2G A2 over R2 times R1. Okay. So now, okay, we can substitute in. We go all the way back to this mess here, right? Okay, well we had, and we don't really care about what's happening here, but we do care about TD or TCD right here, right? So we can write out that phi A to D is equal to this equation, M2 GA2 L2 over J2G, okay, plus we have phi B, and phi B is equal to R over 1 R2, R1 over R2 times phi C, okay, and the phi C was equal to this, so now we have plus R1 R2, okay, and then we have TD, or TCD right here, right, this is the same as TCD, okay, so we have TCD, so this is this M2 GA2, right, and we have another R1 over R2, so that becomes a square, okay, times this L1 over J1G. Let me see. Oh, nope, I made a typo. This is, no, I didn't make a typo, that's right. A2, L1, R1, yep. Okay, so that's how you do it.
Makes sense.
Okay.
The only other question I have is, they don't give us J, so how exactly do you find J1 and J2?
Oh, good question. How do you think?
I assume you use a variation of the equation pi over 2 c to the 4th.
Yeah, exactly. So J1 is going to be, what we give, did I give? I hope I gave. A2, 6 centimeters. But yeah, they have diameters of 1.1 centimeter.
What does it say there?
Right here, have diameters. Okay, so yeah, so it's going to be, yeah, the pi over 2 c to the 4th. And since, well, I guess we had D equals whatever, 1.1 centimeters, I guess. So C is going to be equal to 0.55 centimeters. at least in this particular case. Okay. And then of course that would be 0.0055 meters to probably keep track of everything. Let me close my PowerPoint because as you can see it's doing weird things and I don't know how to stop it from doing those weird things unless... Yes, so how do you calculate G, right?
With the elastic modulus.
That's right.
Shear modulus equation.
That's correct. Well, yes, right. The shear modulus G is equal to E over quantity, over 2 times quantity 1 plus nu. All right. Okay, so now what other questions? Do you have another one? What was the other one you wanted to see? Indeterminate. Okay. Let's see here. Let's find, I had to... this is weird. Okay. Let's hope if I open it up again, it will work. And it doesn't do something like... Well, anyway. So let's see. That was session... Question 6, maybe? Was that the one? Or is there a different one?
Was that the one with like the distributed load?
Let's see. Yeah, I think so. Let's see. Oh, yeah. Here we go.
Yeah, I was wondering maybe we could do like the one in class that kind of went through at the end a little quick. Because I was able to get the one from the home website.
Okay. So let's see. The one from class. There. Updates available. What am I doing? Uh-oh, I just might have crashed it. Let me see. That one. Okay, the indeterminate shafts with mating gears. Yeah, hold on. How are you doing, Matt? Okay, thanks for coming.
Thanks. Are these recorded?
This is recorded if you would like to go back and look at it. It's being recorded right now.
Is it going to be under just Torsion too?
It is, yes, under Torsion 2.
Thank you.
And my Windows or my Microsoft has crashed.
Previous question, the answer had R1 over R2 squared, but
Yes.
we're given R2 over R1.
Yeah,
it's
so it's
just
flipped.
that.
Yeah, it's just flipped. Come on, computer. You can do things. Oh, hold on. Did it just come back to life? I think it just came back to life. Okay, great. Okay, so you're talking about this one? Or this one?
I don't know, whichever one's in the term, this one's fine.
Yeah, okay. So, okay, well, I don't know if I should really. Okay, so here we have that R1 theta or R1 phi 1 is equal to R2 phi 2, right? So that part I think people are now we're getting more comfortable with, right? And then we can say that these are not rotating at the walls. And if we look at equilibrium, we'll get that this TA, whatever that torque is, right, is going to be equal to a torque over here, and we'll get that this TD is going to be equal to a torque over here. And we have the relationships between the contact forces and the torques. Okay, so we can write these out, and we have the opportunity to write T1, T2, and T. But what do we notice there? We notice that, yes?
Just a question. So is T1 equal to the internal torque in the shaft from A to B?
Yes, yes.
And you're saying that that's equal to the torque at
The wall.
Gotcha.
At the wall, yes. Right? This torque at the wall, TA, right, is going to be the internal torque, right? Exactly. Right? And the same thing on the right side. Using equilibrium here, we get a result, though, that has only, well, it does not tell us. It tells us that, you know, we have a relationship between T1 and T2, right? But it doesn't, we can't identify either one of these specifically, right? If you gave me T1, then I can tell you what T2 is. If you gave me T2, I can tell you what T1 is, right? But this is indeterminate in that we've only used equilibrium, and yet we're not able to, we have two unknowns in one equation, essentially. Does that make sense? So we have more unknowns than we have knowns. T is a known here. Right? T is a known, R1, R2, those would be given. Those are knowns as well. So what should we do? Well, we should pull out some constitutive relationships. Okay, so that's what we look at. We say that for this problem, right, I can figure out what the angle of twist is, phi 1, if I know what that torque is, right? So if I know what T1 is, right, or if I know what TA is, then I can figure out what the angle of rotation, phi 1 would be. Does that make sense?
So is phi 1 the rotation of the shaft or of the gear? Or is that the same?
It's going to be, they're connected. The gear is connected directly to the shaft, so they are linked. Okay? Good. And the same is true for the rotation, the phi 2 here, right? It's connected directly to gear C, right? And so the deformation, the twist of the shaft is equal to phi 2. So we can write those two constitutive relationships down. And this is the equation we had from equilibrium. Okay? And we also have this from geometric compatibility, right, from the previous slide. And we had these equations, those are from equilibrium. Okay? And so now we can write out, for example, that TA is equal to this, T plus TD. And we could have written that out actually on the previous slide, right? We could have written this, so we could have, but now what we can do, right, is we can look at these constitutive relationships and plug those in, okay? And what do we see? We see that now we can essentially, remember we had in the previous, or whatever, right here, right, we have T1 and T2, which are equal to TA and TD, right? We needed to know one more thing. We need to substitute an equation in for one of those. And now, by setting these phis up through each other by the radii here, right, now we can essentially say, oh, there's another relationship between T1 and T2 right there. And so we plug that relationship in, except it's in terms of TDs and TAs now instead of, this is T1, this is T2, right? But then we can plug those all in and we can get an equation TA in terms of this, in terms of itself actually, okay? And then we have to rearrange. The only unknown in this equation is TA, right? So then we had to rearrange things and we can figure out what TA is equal to in terms of T. And then we can go back to that original equation that we had here and we can figure out what TD is. Does that make sense? So the general idea, right, with these indeterminate, it's simpler to say than to do, as are many things in life. Once we know the T, or once we realize that we cannot solve a problem with equilibrium by itself, then we gotta look for some type of constitutive relationship. What is constitutive relationship? Something that relates material properties to deformation. Yes. Other questions? Yes.
The section 10, question 4, I'm still getting it wrong.
I don't know what to say. I mean, the equations are in there.
I know. I even put it in the code. Do you think I can show you what I have written down as the equation and you can make sure I wrote it down correctly?
Sure. I mean.
I'm really not sure what I'm doing wrong.
Okay. Let's see. This is Q4, right?
Q4, section 10.
Let's see here. Yeah, we're going to do question 7 at the beginning at 1 o'clock. Okay, so don't worry, we haven't gotten there yet. Okay.
Yeah.
Oh, and all my, all that work I just did, it's all erased. Because the PowerPoint crashed. All right, but I can tell you what the answer was. So it crashed, right?
Yeah.
But you should be able to get it. Let me see if I can find it. Yeah, so what we wrote, right? And you can look at solutions to exam 1, or you could even replay the video that we just lost. But this phi AD, we said would be something like M2 GA2 L2 over J G. Okay. This actually, and this, yeah, the J's are the same, right? J1 and J2 are the same. Plus R1 squared over R2 squared times M2 GA2 L1 over JG.
Okay, that is exactly what I thought.
Yeah, so I don't know then.
L1, just the L1.
Okay. All right. Other questions? This is kind of an opportunity to review things that we've covered for a few more minutes before we shift over into newish material.
That's actually pretty close to my house. That's like maybe like 4 blocks, 5 blocks. Yeah.
That's how my mom. My dad lived there.
Most of the homework questions are very much using solutions that are almost all the way there, okay, with the PowerPoints and then referencing the previous exams, okay. So they're kind of good preparation, like if it's for the next exam, right? The best preparation though in terms of problems is going to be the previous exams. in my opinion. That and understanding the concepts and being able to do these problems as well. And the good thing is that those exams have the solutions as well. conceptual questions though about what we've covered up to this point? Because we've only got 2 minutes or so left. Okay, then I'll go ahead and I'll stop this and I'll get us started with the next set of material.